All right, we left off with Lagrange, and I did not put a Lagrange problem on the test as a bonus, did I? That was partly because I forgot, and it was partly because after I made the test, I was very concerned as to whether or not you would have enough time for the test. So I decided if I threw a bonus on there, it might sidetrack you, and the Lagrange is a long problem to begin with, so I was afraid people were going to go eat 30 minutes of their test trying to do a bonus. So what I'm going to do is I'm going to come up with a problem, and I'll let you take it home as a bonus and turn it in. Something to bump up your score a little bit, you know, no more than like 5 points on the test, but it'll be something, right? All right, so where did we leave off? I know we had done Lagrange. I believe we finished with this problem. No. It was so long ago. Yeah. Yeah, we did do that. Yes, I have not even touched those yet. Yeah, I did everything in my power to get those graded and back to you today. So, yeah. I'll look at those. They're on my to-do list. So, just give me some time. Anytime it's like a bonus, and that was a lot of problems, so I have to kind of look through those, and so just give me some time on that. So yeah, we did finish with that problem. Do you all remember what Lagrange was about? Yeah, I know. What you had was a function where we're trying to find the max and min again, but we were constraining it we weren't leaving its domain wide open, and we weren't constraining the domain to a closed bounded region. We were constraining the domain to an actual curve. And that curve was given to us by what we called the constraint equation. So we had the function, the constraint equation, we were trying to find the max and mins. So what we did was we figured out where the gradient of f was equal to lambda times the gradient of g, and that set us up with a system of equations, and we went and tried to solve those. So everything we had done before, our function was a function of two variables, and our constraint had two variables in it. Now what we're doing is we're extending Lagrange's method out to a function of three variables with a constraint that has three variables in it also. Now what happens in this case is that we lose the geometric meaning of it, I guess. I can't really show you a picture anymore like I did here. So let me remind you, like here was our surface, function two variables. We constrained it. Here's our constraint equation on the ground. We plugged just those points in the blue into the surface. Pull the surface out, take the domain out, and we have these black curves basically that live on our surface, and we were trying to find the highest and lowest points. Now that our function is a function of three variables, we cannot visualize it. All right, so we're going to run out of pictures here. Everything is going to be purely algebraic, and we won't be able to check our answers with a picture. Okay? But the setup is the same. We still have to figure out when the gradient of f is equal to lambda times the gradient of g. We still have to satisfy the constraint equation. Now that our gradient has the three variables in it, the actual gradient has three partial derivatives. Partial with respect to x, y, and z. And then we have our constraint equations. So we have a total of 4 equations and 4 unknowns that we're going to have to determine. So here, example 6, we have 2 examples to work through. All right, so we have f of x, y, z equals 8x minus 4z. Our constraint is x squared plus 10y squared plus z squared equals 5. So here we go. We've got g right here. That's our g equals some constant k. Our f function is here. So we need to figure out these four equations. I need the partial of f with respect to x to be equal to lambda times the partial of g with respect to x. Is this kind of ringing a bell now that I'm writing this out? Okay. Those are the four equations. This first example I think is going to work out real nice. What is the partial of f with respect to x? 8 equals lambda times, what's the partial of g with respect to x? 2x. So we have lambda 2x. And then the partial of f with respect to y is 0 equals lambda times partial of g with respect to y, 20y. And then partial of f with respect to z is negative 4. Lambda partial of g with respect to z is 2z. And then our constraint, we can just rewrite that whole thing again. Questions on that? What could have more than one solution? Yes, you can have more than one solution. Yes. Now, you're saying, if I understand what you're saying, we're looking for an x, y, z, and lambda, right? That make them all true? We could find an x, y, z that make them all true. We could find more than one x, y, and z that make them all true. Is that what you're saying, that we can have more than one solution? Yes, we could.
But at the end, only one of those would be maximum.
Yes, because once we find what the solutions are, we compare them into the, we call this the objective function, the one we're trying to find the maximum of. We plug the values that we get into the objective function, and we compare those answers. The biggest one is our max, the smallest is our min. So even if we had 10 different answers, we still compare them and come down with the two, right, max and min. All right, so which of these equations looks like you want to mess with it? The x and then the y, I heard both. I like the y one, the second equation. Let's say equation 1, equation 2, equation 3, equation 4. I like 2 because if you simplify this, this is just saying lambda y equals 0, which means the only way that I can ever make equation 2 true is if lambda's 0 or if y is 0. That's it. So we've already narrowed down what lambda and y can possibly be. It's either lambda 0 or y 0. Yes? All right, so let's start with that. Suppose lambda equals, I should have put by equation 2 tells me that lambda must be 0 or y must be 0. They could both be 0, but that's a little too restrictive because I want to let one be 0 and then figure out what happens to the rest of the stuff. Suppose lambda is 0. Then what can you tell me? That first equation wouldn't make any sense, would it? That would be equation 1 would tell us that 8 equals what? 0, which it doesn't. So this is a contradiction, right? That's not going to work. So lambda can't be 0, all right? It cannot be 0. Or else, if lambda is 0, our equation number 1 can never be satisfied. All right. So now, instead, suppose y is equal to 0. So what can you tell me if y is 0? Okay, so equation 3 is the only one that has y in it, right? Equation 3, go into equation 3, replace y with 0. You get x squared plus z squared must be 5. Oh, yeah, it's equation 4. Thank you. All right. Well, I've got an equation here. I still have two variables in it, so I can't solve that uniquely. Haven't used equation 1 or 2, or 1 or 3, right? What does equation 1 have in it? Lambda and x. So it has an x. So I could solve this for x, couldn't I? And replace that in here, and I would have a lambda in there, wouldn't I? And I could take my third equation and solve this one for z, and plug that in here, and then I would have a lambda in there, and then I have an equation with just lambdas in it, and then I can figure out what lambda is. Once I know lambda, I can come back and get x and y, or x and z. Yes? But if I'm going to solve this first equation for lambda, for x, sorry, I'm going to have to divide both sides by lambda. So I need to make sure lambda is not 0, right? Okay. So maybe for this suppose, I already know when lambda is 0, you know, the universe collapses, right? So right here on this part right here, I'm just going to add a condition to this, lambda not 0. I think we can say this safely. Y is 0, but I'm going to let lambda be 0, not be 0. So that way we avoid this situation. I can divide through by it. Equation 1 tells me that x is equal to what? 4 over lambda? 8 over 2 lambda. And equation 3 tells me that y is negative 2 over lambda is z? Yeah, I need to change that to a z. Then back to equation 4, x squared would be 4 over lambda squared, plus z squared is negative 2 over lambda squared. That must be equal to 5. So square everything here. 16 over lambda squared plus 4 over lambda squared equals 5. Is that what I heard? Combine these together? 20 over lambda squared equals 5. And then solve for lambda. So lambda would be plus or minus 2. So just move things around, divide through. So lambda is plus or minus 2. We actually have two solutions, right? We have two solutions. So now what I need to do, and I'm kind of running out of space, I would probably indent, and I would say, suppose now lambda is 2, and then later on I'm going to go and let lambda be negative 2. So next page for me. Suppose lambda is 2. Then what is x and what is y? Or no, what is, yeah, I can say what x, y, and z are. Y was 0, right? All of this is still working with the assumption that y was 0. X, we go back to our formula for x that we had, which was right here. X was 4 over lambda, and z was negative 2 over lambda. So I'm still working all within this assumption that y was 0. So x is going to be what? 2, and then z is negative 1. Was z negative 2 over lambda? Is negative 2. So I'm dividing by 2. I'm going to do the next lambda in a second. So here's what I get from this. I'm going to write out x, y, z, lambda. It'll be 2, 0, negative 1, and then lambda is, oh wait, Yeah, 2, 0, negative 1, and then lambda is 2. What do I need to do now? Yeah, let lambda be negative 2. Suppose lambda is negative 2. Then x will be negative 2, y will still be 0, and z will now be positive 1. So we get negative 2, 0, positive 1, and then lambda being negative 2. I personally don't like writing this out like this. This is the way the book does it. A lot of textbooks do it this way because people start to confuse this with like that's a point somewhere, and no, it's just organizing what everything is. All right. Are we done? Go back up here. We said for equation 2 to be true, this is what had to happen. We assumed that lambda was 0. We got this contradiction. And then over here, we let y be 0. When we let y be 0, we were able to come up with values for lambda and checked lambda both ways. We got these 2 points, right? Do I need to go look at these other equations now? No? Why not? We could possibly get this to be 0, right? Right? But think about it this way. In order for Lagrange to work, you must be able to satisfy all 4 equations at the same exact time, simultaneously. The only way you're ever going to satisfy 2, ever, is if lambda was 0 or y was 0. That's it. That's your only options. So that's why I went after that one first, because that had the cleanest attack. And once I look at those 2 options, it doesn't matter, because if this turns out to tell me lambda's 4 or x is 5, it doesn't matter, because the only way this one's going to work is if y is 0 and lambda is 0. Sure, yeah. I mean, but it's by looking at these you can kind of see this. See here, you can't tell me, all you can tell me here is lambda times x is 4, right? That's all you'd be able to say here? 4 equals lambda x. Well, anytime 2 numbers multiply to be 4, these can be infinitely many different things, right? But if 2 numbers multiply to be 0, there's only 2 options. So you could look at each one and then compare. I kind of did that, I guess, a little bit mentally already when I first went after this one. And of course, you wouldn't want to go after that one first because it's just a mess. All right, so now what I need to do is figure out which is the max and which is the min, right? So I need to come back up here, take my results. I need to figure out what is f of, what points am I plugging in there? 2, 0, negative 1, and then I need to plug in 2, negative 2, 0, 1. There we go. So what do you get when you plug it in? 20 what? 20 here? I'm not paying attention. I'm just listening to you. What? 20? And then what about this one? 12? Max and min? I didn't get 12. What is it? I don't know. Negative 20? Should I look or what? What is it? Negative 8. So negative 16, negative 20. There. All right. All right. It's all right. Any questions? Ha 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 ha. That was funny. All right, what should we do next? The next one, boy, look at this one. This one looks like it's going to be a little bit bigger disaster with the partial derivatives, right? I'm just looking ahead here. Let's see what else we've got. Yeah, let's do this one. So f of x yz equals x squared y squared z squared. You know, one of the biggest differences I usually see in students that are doing really, really well and those who aren't, believe it or not, the ones who are doing really well usually are not trying to work full-time jobs. That's usually the biggest factor, is how much you are trying to do outside of school. Because a true full-time student, like all these A&M students I was talking about, I almost guarantee you every one of them during the fall and spring semester are not going and working. They are studying. That's what a full-time student is supposed to do. Study, work, hours outside of the class. So, all right. What do we need? 4 equations? How do I know it's 4, not 3? That's right. There's going to be 3 partials. So because I have 3 variables, right, I know that I'm going to have the 3 partials, and then the 4th one's always the constraint. So let me write down the partials. Oh, man. Seriously? It's 2x y squared z squared equals lambda 2x. Is that right? Oh, man, this is going to suck. Okay, let's see, this one will be x squared 2y z squared equals lambda times 2y. And the last one will be x squared y squared times 2z equals lambda times 2z. And then our constraint. They all look alike. What did we do last time they all looked alike? That's right. We made them look alike, right? We made it happen. This one is 2x y squared z squared. This one is x squared 2y z squared. So I need to make all of them have 2x squared y squared z squared. Right? If I can make them all 2x squared y squared z squared, then they're all the same. I can set them equal to each other and everything will be great. So to do that, I have to multiply this one by x on both sides, this one by y on both sides, this one by z on both sides. If I do that, I have to promise that x, y, and z will never be what? 0. Now, they can't all be 0, can they? 0, 0, 0? Because then my 4th constraint equation wouldn't be satisfied. Could you have one of them be 0? Yes, but not all of them simultaneously. So here are my 4 equations. Suppose x and y and z are all not 0. Then what I have, let's see, I multiply this first equation by x, and I get 2x squared y squared z squared becomes 2 lambda x squared. And do the second one. 2x squared y squared z squared equals 2 lambda y squared. And finally, from the third one, I'm sorry? What did I do? So I'm taking the first equation, I'm multiplying x on both sides. Second equation, multiplying y on both sides. Third equation, multiplying z on both sides. And that gives me 3 new equations. My equation 1, my equation 2, my equation 3. And they're all the same now, right? Like this left side's the same as that left side and that left side. Now what makes that good is I can set them all equal to each other now, right? So if I set equation 1 equal to equation 2, it gives me that 2 lambda x squared must equal 2 lambda y squared. What should I do here? Divide by 2? Good. Move everything to one side and get rid of the 2. Factor a lambda out. X squared minus y squared is difference of squares. So we get three different things that could happen here, right? Lambda could be 0, x could be y, or x could be negative y. So we're going to have 3 different supposes just from this one thing. Questions, though? Yes. Plus or minus y, though, because of the square root. Yeah. Which would give us the same thing as we would get here. No, that's all right. I mean, either way it would work, which is a good thing about algebra. Usually, right, multiple paths should lead you to the same result. Okay, those are the 3 things that have fallen out of this one thing, right? I said, hey, suppose x, y, and z are all not 0. Let's see what happens. We get those 3. Let's start with lambda being 0. Suppose lambda is 0. What would happen? Go back to the very beginning of the problem. If lambda was 0 right here, you would have that 2x y squared z squared would have to be equal to 0, which would mean what? One of those would have to be 0. But we said, assume that none of them are 0. And at the very end, we're saying lambda 0 means that one of those had to be 0, which means that lambda can't be 0. So I'm going to say, suppose lambda is 0. Equation 1 would imply that 2xy squared z squared must equal 0, which implies that x or y or z equals 0, which is a contradiction of what we assumed to get here. Does that logic make sense? All right. Suppose that y equals x. What would that tell us? Anything good? No? What if y was x in here? What's that? 2x cubed z squared would equal lambda times 2x? Yeah. Yes. To get to... I did equation 1 and 2. I set those 2 equal to each other. Absolutely. Absolutely, we could. Because the only assumption that we've made here, right, is that all these can't be 0. And what we've deduced from that is these relationships, and this one doesn't have to be, that one can't happen, right? So why not come back up here and let equation 1 be equal to equation 3, right? And work with that one? Or you could say equation 2 equals 3. It doesn't matter. But you want to go 1 and 3? And that's fine. Correct. And then they're all related to each other, right? Okay. So I'm going to go right here. I'm going to be like, I'm not sure if this is getting me anywhere. But let me back up and go set equation 1 and 3 together. Equation 1 equals equation 3. I think the algebra there is almost identical, isn't it? It's, yeah, it's identical. Help me out. What is it? 2 lambda x squared equals 2 lambda z squared. And without actually going through that, are we okay just to say that tells us lambda is 0, x is equal to z, and x is equal to negative z? It's the same exact factoring as before. And we can throw out the lambda 0 because it's all under the same assumption that x, y, and z were not all 0. So this would mean that x could be, let's look at these different scenarios because there are some scenarios here. We could have, if we let x be x, then y could be what? X also, and z could also be x. That's one thing that could happen. I could also let x be equal to x, then the y could be negative x, and the z could be negative x, or x, or x, right? I mean, there's different scenarios here. We could have all the different combinations of positive and negative. We could have, positive, 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 negative, positive, positive, negative, negative, right? All these different things. But let's go to the constraint equation, right? We haven't gone to the constraint. What's our constraint? Equation 4 says x squared plus y squared plus z squared equals 1. No? But if y is x and z is x, or even negative x, doesn't matter, I'm going to square them, right? This just means that I have x squared plus x squared plus x squared equals 1, so 3x squared equals 1, which means that x squared equals 1/3, which means that x equals plus or minus 1 over root 3. Right? So what's y then? Well, y could be plus or minus 1 over root 3, and z could be plus or minus 1 over root 3. There's all those different combinations, right? So I would need to go look at this now, and I have a bunch of things to look at. I have 1 over root 3, 1 over root 3, 1 over root 3. Did we ever really figure out what lambda was? Not really, but I don't care. Remember I said if I can get what x, y, and z are and don't need lambda. Sometimes we need lambda to get x, y, and z, but if we don't, then who cares? Don't go back and find it. And then each of these could be plus or minus. And what am I supposed to do with those values? To try and figure out where this max thing is? Take them and plug them into the original function, right? The original function. The original function, if you don't recall, was x squared, y squared, z squared, wasn't it? So if I just square each of these, thank goodness that wipes out the plus and minus scenarios. So it's just 1/3 times 1/3 times 1/3? 1/27. 1/27. Is that a max or a min? Test another point? We could, but it has to live on our constraint. 100? Any point that lives on there, 100, right? So I can test 1, 0, 0. If I test 1, 0, 0, I get f of 1, 0, 0 is equal to 0, which means that this is a max, right? What's the minimum then? What's the smallest this function can be on that constraint? What is the smallest value this function can be ever? Ever, ever. 0, right? Does that happen on your constraint? Isn't this our constraint? This satisfies our constraint, doesn't it? So that does live on our constraint? So does it achieve its minimum? It does, right? Well, I guess what I'm getting at is we don't really need to go test to see what the minimum value is. The minimum value is 0. It's x squared, y squared, z squared. It can never be negative, right? The least it could ever be is 0. The question is, does it happen on our constraint? We already showed it does, right? So the maximum value of this function on that constraint is 1/27th. It happens at all the different variations of these points. And the minimum value of this function is 0. Hope that makes sense. All right, let's take a look at looking at example 8. Find the maximum volume of a rectangular box with a double bottom if it is to be made from 81 square feet of cardboard. What are its dimensions? So this is a problem that you could have done back in like calculus. This would be somewhat of a calculus problem. And we're just here to show that you can be done in this class also, all right? A different approach. Find the maximum volume of a rectangular box with double bottom. Everyone have the problem? So I'm going to get rid of it and go to figuring it out. So I have a rectangular box made out of cardboard. It has a double bottom, meaning when they manufactured it, they put a double layer of cardboard on the bottom for strength, I guess. But let's assume that all the sides are covered, okay? So there's a surface on all sides of this rectangular box, but the double bottom. I want to try and find the greatest volume that I can get out of a box like this if it's constructed from 81 square feet of cardboard, okay? What is it that I'm trying to find the maximum of? The maximum volume. That is our objective function. That's the thing we're trying to find the highest and lowest of, right? Well, in this case, the highest. So I'm trying to find the volume. What is the volume, or maximum volume? What is the volume of a rectangular box? Length times width times height, right? Why don't I call this x? Why don't I call this y? And why don't I call this z? Did you agree that the volume is a function of those three variables? And it is exactly x times y times z? Right? Do you all agree with that? Okay. That's the volume of any box. But this box is special. The way it was constructed, 81 square feet of cardboard with the double bottom, there's some constraint as far as how I can build it, right? That's going to become our constraint equation. But what is it? I mean, what is it? We're constrained by the surface area, aren't we? It can only be 81 square feet. So tell me, what is the surface area of this box? I'm just going to do it in blue over here. What's the area? I'm going to call it A instead of surface area. What's surface area? So we have this front side, that's x times z, and then the back side equivalent to that, right? So 2xz. And then we have the side over here, one of those, right? And then another one on the side there. So that's four of those. I mean, not four, two of those. Two yz's. Y'all still okay with that? Plus, now let's do the top. What's this right here? What's the area of that top piece? XY, how many of those do I have? 3. Because there's a double bottom, remember? So we have the top, and then the XY on the bottom, it was double made. So we have 2 of those. Does that make sense? The cardboard, we're counting it twice. We have the top piece, and then the bottom piece, and then they doubled it up. So they put another one underneath that, you know, and then double stacked it. Okay. Yeah? XZ, yes, should be XZ. Thank you. Yeah. X times the height, which was Z. There's 2 of them. And then the side here, Y times Z. There's 2 on each, 1 on each side. And then our XY, which is X times this side. Yeah. Everyone agree with that? That's the area. What's that? Remember the problem said it had to have a double bottom? So we have the cardboard on the top of the box. That's one of the XYs. Then the bottom of the box, another XY, but then they double made the bottom, so another piece down there. Who does that? No one does that, but it's just for fun. That's what the problem says. Okay, so I would like to somehow make this my constraint equation because I'm trying to find the biggest this can become, right? Well, to constrain that, I have a constraint, right? That has to be what? 81 feet. So I know that this must equal 81. Let me scratch that A out of there. I don't want that in the front anymore. Does everyone see this is our constraint? It's our constraint equation right there. So we have over here in yellow, we have our F, right? Our F function. And then over here, everything on the left side of this equation, that's our G. A function constrained, right? Function with a constraint equation, Lagrange. Gradient of F has to equal to lambda gradient G. The way you do this in like a calculus class is you would try and get everything in terms of X. And that actually would be very difficult to do here. We would try and look at that function up there as a function of X, then you take the derivative and try and find the maximum. It could be a real mess, the algebra of it. Let's see if this one's messy. I'm not saying this one's not going to be messy. I'm just saying that we can use this method. Let's hope for the best here. I'm going to have 4 equations. Start giving myself a little more room for the first ones. Oh man, but that constraint's pretty long. All right, my first one is what? YZ equals, shit, it's more than one term, isn't it? Okay, 2Z plus 3Y. Crap, there's no way around that. Everyone got that? That's partial of F with respect to X equals lambda partial of G with respect to X. And then the next one will be XZ equals lambda 2Z. That's it? Oh no, 2X. I'm doing with Y. Yeah. 2Z plus 3X. Next equation will be XY equals lambda. Now with respect to Z, 2X plus 2Y. And then our constraint. I'm just going to say constraint, okay? Constraint equation. I don't feel like rewriting that whole thing. Man. We solve for Z. Yeah, let's keep that in mind. X, Y, and Z can't be 0 here, right? Because if X, Y, or Z, if any one of them is 0, our volume is 0. And definitely we don't want a 0 volume box, right? You could do the matching again, where you do X, Y, and Z again to make them look the same. Solving this for Z, the only issue I find is that Z is over here also. So you would actually have to get the z out of here by distributing and then move all the z's to one side, and right? I kind of like the idea of trying to make them match again and setting them equal, but I'm not saying it's going to work. Could we solve each of them for lambda? Set them equal to each other? Good. As long as you promise me that this isn't 0, because I'm going to divide through by it. Will that ever be 0? No, because the only way that's going to be 0 is if they're both 0 or one of them's negative. And it can't have negative because all your x, y's, and z's have to be positive. So, I mean, all these different things you have to think through, and how do you want to do it? Because I'm open to anything. You want to solve them for lambda? And then set them equal to each other? All right. Fine with me. We haven't done that, so if I solve this for lambda, it's lambda equals yz over 2z plus 3y. Now I'm becoming a little more loose with my notation because I think I've been through this now enough. Like I should really write, like suppose 2z plus 3y is not 0, or somehow convince you it won't be, right? Say x, y, and z all have to be greater than 0. Therefore, this is okay. Lambda is xy over 2x plus 2y. Set any of these equal to each other. So let's try equation, or no. Yeah, I'll say equation 1 equal to equation 2. What I mean by that is I'm setting this lambda to this lambda. Let's see if this helps. I don't know. What are we going to do here? Yeah, you get rid of the z. Don't want to get rid of z? Now what? We can do that because z can't be 0, right? Okay. Like a cross multiply type thing, right? So we get like 2yz plus 3xy equals 2xz plus 3xy. Hey! Is that right? Do those xy's cancel? And we're left with yz equals xz, aren't we? Can I divide by z again? Y must be x. Hey, now that is a result right there, right? Y must be x. Now, what do you think I should maybe do now? Do the same for like these two lambdas maybe, or the first lambda and the last one? You want to go 2 and 3 this time? I'll try that. Let me do equation 2 and equation 3. Meaning the second lambda with the first one. Or the second one with the third one. It's nice when the algebra works out that way, but I'm not quite sure it's going to happen here. Because in the last one we had the same coefficients, didn't we? 2 and 3. Right, we had 2 and 3 and 2 and 3. Things worked out real good. Let's just see what happens. Can I kill anything off? The x's? Okay, I multiply both sides, so 2xz plus 2yz equals 2yz, yes. And then plus 3xy. 2yz's cancel. And now, what? Get rid of the x's? So 2z equals 3y. or z equals 2/3 y. But y was what? Y has to be x. So I could replace z with 2/3 x, right? I could replace y with x and just leave x as x and go to my constraint, can't I? So now let's go to my constraint. Z is 2/3. No, 3/2. What the hell? Thank you. 3/2. I divided wrong. Minus 18. See, here's the deal. Listen, I serve my time. See, I've been on that side. I'm allowed to make little mistakes now and then. All right. I sat in the room for 2.5 hours and took a test. I had to stand in front of people and defend my ideas. So I have the stamp of approval. I'm allowed to, right? I guess I can feel that way. All right. So what now? Yeah, my constraint, right? Now my constraint, I don't know where the hell that is. It's 2xz, 2yz, 3xy, 81. Okay, now I'm going to replace every x, well, I'm going to leave my x's alone, replace every z with 3/2 x, every y with x. Was it 3/2 or it's 3/2? Yeah, I fixed it. Right. I had made a big mistake. Plus 3x times x equals 81. All right. Double check that. I think I got it all there. 2xz, yz, xx. Nice, those two. So I have 3x squared, 2 plus 3x squared plus 3x squared equals 81. So 9x squared equals 81. X squared is 9. X is 3. Or -3. But can't be negative, right? So if x is 3, what's y? 3, and then what's z? 3/2 times 3, right? 9/2? 4.5? Hmm? Is that a max or a min? Well, max. I mean, right? I mean, minimum box we're going to get is 0. So this is going to be obviously a max. Now, what's the actual volume of this box? Just multiply those together, right? 3 times 3 times 9/2. So 81/2. The maximum volume would be 81 over 2 cubic feet. That wasn't terribly bad, was it? At least we didn't have to like get somehow, z in terms of x and y and try and find, yeah, I mean, we could have done this using the calculation of d. Remember how we did the d, capital D, find max min? We could have done it that way, but we would have had to turn everything into a function of x and y only, which would have been solving this constraint for z and then plugging that into the volume function. Yeah, x can't be negative. Let me see something here. Let's see if it matches up to what my thing does here. X times y times z, and it was. Can you read that again? 2x times, what was the constraint? 2xz, 2y times z, 3x times y, and that equals 81. Whoa. 81. Yeah, we never found lambda, but it was 3/4, negative 3/4. So here's the maximum. See, the program doesn't know that x and y can't be negative and z can't be negative, but this is your 81 halves right there. It happens at 339 halves. So that just verifies that our algebra was good. All right, we're almost done. Look at this one right here. Find the point or points on the sphere x squared plus y squared plus z squared equals 4, closest and farthest from the point 3, 1, negative 1. So there's planet Earth, right? And there is something out there. And we are trying to find the 2 points, one which is closest to that point and one which is furthest from that point, but has to also live on that sphere. Make sense geometrically? Yeah? Projection? Well, like a projection vector. The only problem would be you would need you know that these, I guess you know that these two points lie on a line that goes through the center of the sphere, right? Has to. So you could you know the center of the sphere from the equation. So you can come up with a vector going from the point to the center of the sphere. It's just what's the projection though? Like you said, if you try and grab a point over here, there's a curve, so it's curving away. So if it was a plane, of course you could do it. But that's a good thought. It's not going to be quite as easy as the plane. So let's look at it this way. Let's say that the projector up there is the point, right? And I'm trying to find the shortest distance between that or shortest and furthest distance from this sphere, right? Forget the sphere is here, all right? Forget the sphere is here. If I say what is the distance from that projector to any point, then I can move that point anywhere I want, right? And I have a different distance no matter where I put it. And so the distance, there's a formula for the distance between 2 points. So that distance changes as I move that point around. There is no maximum or minimum if I'm allowed to move this point anywhere, right? But if I fix and I tell you this point has to live on the sphere, isn't the sphere the constraint? The sphere is the constraint. The point is just living anywhere. The distance is well defined, but now I say you can't live anywhere. Constrain yourself to the sphere. That means that this equation right here is our constraint. The thing we're trying to find the maximum and minimum of is the distance between that point and what? That point and any point in three-dimensional space, right? That's our function we're trying to optimize. The distance between that point and any point in 3D space. Then constrain it. What a lot of people do in a problem like this is they try and come up with a function that represents the distance from that point to the point on the sphere. You don't need to worry about the sphere. The sphere comes in as the constraint. You just need to get a formula for the distance between the projector and an arbitrary point. Kind of like with here, when we drew the box, right? Initially, we came up with a volume function, and there was no constraint. X, Y, and Z could be whatever they wanted. Then we brought in the restriction. So let's find our function that defines the distance between an arbitrary point, X, Y, Z, and the specific point here, which is the point 3, 1, negative 1. What is the distance between those 2 points? I'll call it D. Will be equal to the square root of x minus 3 squared plus y minus 1 squared plus z plus 1 squared. That's the distance formula for the distance between 2 points in three-dimensional space. One of the first things we ever studied in here. That's the distance between an arbitrary point and the point that we were talking about. So this d is like our function, like our volume function was. Now, do you remember in Cal 1 we said if we ever try to maximize or minimize distances, that instead of looking, because they usually involve the square root, then we usually look at the distance squared instead? Do y'all remember that in Cal 1, doing that? It helps us when we take our derivative to not have to worry about the square root. So I'm going to look at d squared instead. And so this is what I'm going to call my capital D of x, y, z. So capital D is the distance, but it's squared. Just keep that in mind. We'll have to take the square root at the very end. Do you know what the constraint equation is? Okay. That's your bonus problem to be turned in next class. Finish it up and turn it in next class, all right? Yes, I think, yes. Yes. F, like what's F and what's G? Yeah. Yeah, it's example 9. By the way, I don't remember, on your notes, it might actually show minimum distance and maximum distance. Okay, it might show you the answer here. If I remember correctly, there was a problem when I coded this up and something was off. I don't remember. Those might be right, but they may not be right. So if you're trying to get the answer at the very end, and you're like, man, I'm not getting 1.315, don't go off of that, all right? Because it may be off. I think I went and fixed it, but I don't recall. All right, everyone understand? That's a bonus question to be turned in next class, beginning of class. No exceptions, no late work accepted. I'll add up to 5 points onto your test. Go where? My work? There was no minimum value because we weren't asked for a minimum value. We were asked to find the maximum volume that we could get out of this box. Yeah, it turned out to be 81 halves for the volume. And then the dimensions of the box were given by this. All right. Adios.